My name is Mumshad Monambeth, and we are going through the certified Kubernetes Administrators course. In this section, we discuss about application lifecycle management. We start at rolling updates and rollbacks, the different ways to configure applications, scale applications, before finally looking at the primitives. Hello and welcome to this lecture. In this lecture, we will talk about updates and rollbacks in a deployment. Before we look at how we upgrade our application, let's try to understand rollouts and versioning in a deployment. When you first create a deployment, it triggers a rollout. A new rollout creates a new deployment revision. Let's call it revision 1. In the future, when the application is upgraded, meaning when the container version is updated to a new one, a new rollout is triggered and a new deployment revision is created, named revision 2. This helps us keep track of the changes made to our deployment and enables us to roll back to a previous version of deployment if necessary. You can see the status of your rollout by running the command kubectl rollout status followed by the name of the deployment. To see the revisions and history of rollout, run the kubectl rollout history command followed by the deployment name, and this will show you the revisions and history of our deployment. There are two types of deployment strategies. Say, for example, you have 5 replicas of your web application instance deployed. One way to upgrade these to a newer version is to destroy all of these and then create newer versions of application instances. Meaning, first destroy the 5 running instances and then deploy 5 new instances of the new application version. The problem with this, as you can imagine, is that during the period after the older versions are down and before any newer version is up, the application is down and inaccessible to users. This strategy is known as the recreate strategy, and thankfully this is not the default deployment strategy. The second strategy is where we do not destroy all of them at once. Instead, we take down the older version and bring up a newer version one by one. This way the application never goes down and the upgrade is seamless. Remember, if you do not specify a strategy while creating the deployment, it will assume it to be rolling update. In other words, rolling update is the default deployment strategy. So we talked about upgrades. How exactly do you update your deployment? When I say update, it could be different things, such as updating your application version by updating the version of Docker containers used, updating their labels, or updating the number of replicas, etc. Since we already have a deployment definition file, it is easy for us to modify this file. Once we make the necessary changes, we run the kubectl apply command to apply the changes. A new rollout is triggered and a new revision of the deployment is created. But there is another way to do the same thing. You could use the kubectl set image command to update the image of your application. But remember, doing it this way will result in the deployment definition file having a different configuration. So you must be careful when using the same definition file to make changes in the future. The difference between the recreate and rolling update strategies can also be seen when you view the deployments in detail. Run the kubectl describe deployment command to see the detailed information regarding the deployments. You will notice when the recreate strategy was used, the events indicate that the old replica set was scaled down to 0 first, and then the new replica set scaled up to 5. However, when the rolling update strategy was used, the old replica set was scaled down one at a time, simultaneously scaling up the new replica set one at a time. Let's look at how a deployment performs an upgrade under the hood. When a new deployment is created, say to deploy 5 replicas, it first creates a replica set automatically, which in turn creates the number of pods required to meet the number of replicas. When you upgrade your application, as we saw in the previous slide, the Kubernetes deployment object creates a new replica set under the hood and starts deploying the containers there. At the same time, taking down the pods in the old replica set following a rolling update strategy. This can be seen when you try to list the replica sets using the kubectl getReplicaSets command. Here we see the old replica set with 0 pods and the new replica set with 5 pods. Say for instance, once you upgrade your application, you realize something isn't very right. Something's wrong with the new version of build you used to upgrade. So you would like to roll back your update. Kubernetes deployments allow you to roll back to a previous revision. To undo a change, run the kubectl rollout undo command followed by the name of the deployment. The deployment will then destroy the pods in the new replica set and bring the older ones up in the old replica set, and your application is back to its older format. When you compare the output of the kubectl getReplicaSets command before and after the rollback, you will be able to notice this difference. Before the rollback, the first replica set had 0 pods and new replica set had 5 pods, and this is reversed after the rollback is finished. To summarize the commands real quick, use the kubectl create command to create the deployment, get deployments command to list the deployments, apply and set image commands to update the deployments, and rollout status command to see the status of rollouts, and rollout undo command to roll back a deployment operation. Hello and welcome to this lecture. My name is Mumshad Manambeth. In this section, we will talk about commands and arguments in a pod definition file. This is not listed as a required topic in the certification curriculum, but I think it's important to explain as it is a topic that is usually overlooked. Let's first refresh our memory on commands in containers and Docker. We will then translate this into pods in the next lecture. In this lecture, we will look at commands, arguments, and entry points in Docker. Let's start with a simple scenario. Say you were to run a Docker container from an Ubuntu image. When you run the docker run Ubuntu command, it runs an instance of Ubuntu image and exits immediately. If you were to list the running containers, you wouldn't see the container running. If you list all containers, including those that are stopped, you will see that the new container you ran is in an exited state. Now, why is that? Unlike virtual machines, containers are not meant to host an operating system. Containers are meant to run a specific task or process, such as to host an instance of a web server or application server or a database, or simply to carry out some kind of computation or analysis. Once the task is complete, the container exits. A container only lives as long as the process inside it is alive. If the web service inside the container is stopped or crashes, the container exits. So who defines what process is run within the container? If you look at the Docker file for popular Docker images like nginx, you will see an instruction called cmd, which stands for command, that defines the program that will be run within the container when it starts. For the nginx image, it is the nginx command. For the MySQL image, it is the mysqld command. What we tried to do earlier was to run a container with a plain Ubuntu operating system. Let us look at the Docker file for this image. You will see that it uses bash as the default command. Now, bash is not really a process like a web server or database server. It is a shell that listens for inputs from a terminal. If it cannot find a terminal, it exits. When we ran the Ubuntu container earlier, Docker created a container from the Ubuntu image and launched the bash program. By default, Docker does not attach a terminal to a container when it is run. And so the bash program does not find a terminal, and so it exits. Since the process that was started when the container was created finished, the container exits as well. So how do you specify a different command to start the container? One option is to append a command to the Docker run command, and that way it overrides the default command specified within the image. In this case, I run the docker run Ubuntu command with the sleep5 command as the added option. This way, when the container starts, it runs the sleep program, waits for 5 seconds, and then exits. But how do you make that change permanent? Say you want the image to always run the sleep command when it starts. You would then create your own image from the base Ubuntu image and specify a new command. There are different ways of specifying the command. Either the command simply as is in a shell form or in a JSON array format like this. But remember, when you specify in a JSON array format, the first element in the array should be the executable. In this case, the sleep program. Do not specify the command and parameters together like this. The command and its parameters should be separate elements in the list. So I now build my new image using the docker build command and name it as Ubuntu Sleeper. I could now simply run the docker Ubuntu Sleeper command and get the same results. It always sleeps for 5 seconds and exits. But what if I wish to change the number of seconds it sleeps? Currently, it is hard-coded to 5 seconds. As we learned before, one option is to run the docker run command with the new command appended to it. In this case, sleep10. And so the command that will be run at startup will be sleep10. But it doesn't look very good. The name of the image, Ubuntu Sleeper, in itself implies that the container will sleep. So we shouldn't have to specify the sleep command again. Instead, we would like it to be something like this. Docker run Ubuntu Sleeper 10. We only want to pass in the number of seconds the container should sleep, and the sleep command should be invoked automatically. And that is where the entry point instruction comes into play. The entry point instruction is like the command instruction, as in you can specify the program that will be run when the container starts. And whatever you specify on the command line, in this case 10, will get appended to the entry point. So the command that will be run when the container starts is sleep10. So that's the difference between the two. In case of the CMD instruction, the command line parameters passed will get replaced entirely, whereas in case of entry point, the command line parameters will get appended. Now, in the second case, what if I run the Ubuntu Sleeper image command without appending the number of seconds? Then the command at startup will be just sleep, and you get the error that the operand is missing. So how do you configure a default value for the command if one was not specified in the command line? That's where you would use both entry point as well as the command instruction. In this case, the command instruction will be appended to the entry point instruction. So at startup, the command would be sleep5 if you didn't specify any parameters in the command line. If you did, then that will override the command instruction. And remember, for this to happen, you should always specify the entry point and command instructions in a JSON format. Finally, what if you really want to modify the entry point during runtime? Say, from sleep to an imaginary sleep 2.0 command. Well, in that case, you can override it by using the entry point option in the docker run command. The final command at startup would then be sleep 2.0 10. Well, that's it for this lecture, and I will see you in the next. Hello! In this lecture, we will see how to set an environment variable in Kubernetes. Given a pod definition file, which uses the same image as the Docker command we ran in the last lecture. To set an environment variable, use the env property. Env is an array, so every item under the env property starts with a dash indicating an item in the array. Each item has a name and a value property. The name is the name of the environment variable made available with the container, and the value is its value. What we just saw was a direct way of specifying the environment variables using a plain key-value pair format. However, there are other ways of setting the environment variables, such as using config maps and secrets. The difference in this case is that instead of specifying value, we say value from, and then a specification of config map or secret. We will discuss about config maps and secret keys in the upcoming lectures. That's it for this lecture, and I will see you in the next. In this lecture, we will discuss how to work with configuration data in Kubernetes. In the previous lecture, we saw how to define environment variables in a pod definition file. When you have a lot of pod definition files, it will become difficult to manage the environment data stored within the various files. We can take this information out of the pod definition file and manage it centrally using configuration maps. Config maps are used to pass configuration data in the form of key-value pairs in Kubernetes. When a pod is created, inject the config map into the pod so the key-value pairs are available as environment variables for the application hosted inside the container in the pod. There are two phases involved in configuring config maps. First, create the config map, and second, inject them into the pod. Just like any other Kubernetes object, there are two ways of creating a config map. The imperative way, without using a config map definition file, and the declarative way, by using a config map definition file. If you do not wish to create a config map definition file, you could simply use the kubectl create config map command and specify the required arguments. Let's take a look at that first. With this method, you can directly specify the key-value pairs in the command line. To create a config map of the given values, run the kubectl create config map command. The command is followed by the config name and the option from literal. The from literal option is used to specify the key-value pairs in the command itself. In this example, we are creating a config map by the name appconfig with a key-value pair of app color equals blue. If you wish to add additional key-value pairs, simply specify the from literal options multiple times. However, this will get complicated when you have too many configuration items. Another way to input configuration data is through a file. Use the from file option to specify a path to the file that contains the required data. The data from this file is read and stored under the name of the file. Let us now look at the declarative approach. For this, we create a definition file just like how we did for the pod. The file has an API version, kind, metadata, and instead of spec, here we have data. The API version is v1, the kind is config map. Under metadata, we specify a name for the config map. We will call it appconfig. Under data, add the configuration data in a key-value format. Run the kubectl create command and specify the configuration file name. So that creates the appconfig config map with the values we specified. You can create as many config maps as you need in the same way for various different purposes. Here I have one of my applications, other for MySQL, and another one for Redis. So it is important to name the config maps appropriately as you will be using these names later while associating it with pods. To view config maps, run the kubectl get config maps command. This lists the newly created config map named appconfig. The describe config maps command lists the configuration data as well under the data section. Now that we have the config map created, let us proceed with step 2, configuring it with a pod. Here I have a simple pod definition file that runs my simple web application. To inject an environment variable, add a new property to the container called env_from. The env_from property is a list, so we can pass as many environment variables as required. Each item in the list corresponds to a config map item. Specify the name of the config map we created earlier. This is how we inject a specific config map from the ones we created before. Creating the pod definition file now creates a web application with a blue background. What we just saw was using config maps to inject environment variables. There are other ways to inject configuration data into pods. You can inject it as a single environment variable, or you can inject the whole data as files in a volume. We will look at some of these options in the coding exercises that accompany this lecture. So head over to the coding exercises section and practice viewing, configuring, and troubleshooting environment variables on a live Kubernetes environment. Hello and welcome to this lecture on secrets in Kubernetes. Here we have a simple Python web application that connects to a MySQL database. On success, the application displays a successful message. If you look closely into the code, you will see the host name, username, and password hard-coded. This is of course not a good idea. As we learned in the previous lecture, one option would be to move these values into a config map. The config map stores configuration data in plain text format. So while it would be okay to move the host name and username into a config map, it is definitely not the right place to store a password. This is where secrets come in. Secrets are used to store sensitive information, like passwords or keys. They're similar to config maps, except that they're stored in an encoded format. As with config maps, there are 2 steps involved in working with secrets. First, create the secret, and second, inject it into pod. There are 2 ways of creating a secret: the imperative way, without using a secret definition file, and the declarative way by using a secret definition file. With the imperative method, you can directly specify the key value pairs in the command line itself. To create a secret of the given values, run the kubectl create secret generic command. The command is followed by the secret name and the option from literal. The from literal option is used to specify the key value pairs in the command itself. In this example, we are creating a secret by the name appSecret with a key value pair db_host equals MySQL. If you wish to add additional key value pairs, simply specify the from literal options multiple times. However, this could get complicated when you have too many secrets to pass in. Another way to input the secret data is through a file. Use the from file option to specify a path to the file that contains the required data. The data from this file is read and stored under the name of the file. Let us now look at the declarative approach. For this, we create a definition file, just like how we did for the config map. The file has API version, kind, metadata, and data. The API version is v1, kind is secret. Under metadata, specify the name of the secret. We will call it appSecret. Under data, add the secret data in a key value format. However, one thing we discussed about secrets was that they are used to store sensitive data and are stored in an encoded format. Here we have specified the data in plain text, which is not very safe. So while creating a secret with a declarative approach, you must specify the secret values in an encoded format. So you must specify the data in an encoded form like this. But how do you convert the data from plain text to an encoded format? On a Linux host, run the command echo-n followed by the text you're trying to convert, which is MySQL in this case, and pipe that to the base64 utility. To view secrets, run the kubectl get-secrets command. This lists the newly created secret along with another secret previously created by Kubernetes for its internal purposes. To view more information on the newly created secret, run the kubectl describe secret command. This shows the attributes in the secret, but hides the value themselves. To view the values as well, run the kubectl get secret command with the output displayed in a YAML format using the -o option. You can now see the encoded values as well. Now, how do you decode encoded values? Use the same base64 command you used earlier to encode it, but this time add a decode option to it. Now that we have secret created, let us proceed with step 2, configuring it with a pod. Here I have a simple pod definition file that runs my application. To inject an environment variable, add a new property to the container called env_from. The env_from property is a list, so we can pass as many environment variables as required. Each item in the list corresponds to a secret item. Specify the name of the secret we created earlier. Creating the pod definition file now makes the data in the secret available as environment variables for the application. What we just saw was injecting secrets as environment variables into the pods. There are other ways to inject secrets into pods. You can inject as single environment variables or inject the whole secret as files in a volume. If you were to mount the secret as a volume in the pod, each attribute in the secret is created as a file with the value of the secret as its content. In this case, since we have 3 attributes in our secret, 3 files are created. And if we look at the contents of the db password file, we see the password in it.
So here are some things to keep in mind when working with secrets. First of all, note that secrets are not encrypted. They're only encoded, meaning anyone can look up the file that you created for secrets or get the secret object and then decode it using the methods that we discussed before to see the confidential data. So remember not to check in your secret definition files along with your code when you push to GitHub or something. So there are lots of repositories already on GitHub where users have pushed their secret objects along with their code, the rest of the code. The thing is, you could easily get those secret objects, read them, and then just decode them using the base64 option that we just discussed. And you can get to see what the underlying passwords are. So keep that in mind. Another note is that the secrets are not encrypted in etcd, so none of the data in etcd is encrypted by default. So consider enabling encryption at rest. So there is a document about it. Okay, so this is a document about encrypting secret data at rest. So it uses something called as an encryption configuration. This is an object that you must create, and you will be able to pass this through as an option to the kubeAPI server. So you create the encryption configuration file and then pass it through, and basically you can target specific resources here. So if you only want to encrypt secrets, then you pass it in here like this and provide a base64 encoded object that will be used to encrypt the secret. So yeah, I'll record a demo of this entire process and add it as a video, but I'm just pointing that out here. Also note that anyone able to create pods or deployments in the same namespace can access the secrets as well. So once you create a secret in a particular namespace, if anyone with access to creating a pod or deployment in the same namespace just goes in and creates a pod or deployment and uses that same secret, then they are able to see the secret objects mounted onto those pods. So you should consider configuring role-based access control to restrict access. And finally, consider third-party secret providers such as AWS provider or Azure provider or GCP provider or the Vault provider. This way, the secrets are stored not in etcd but in external secret provider, and that those providers takes care of most of the security. So configuring those are advanced topics for this course, and we will discuss this in the Certified Kubernetes Security Specialist course. Well, that's all for now. Head over to the labs and practice working with the basics of secrets. Okay, so in this video, we're going to look into encrypting secret data at rest. So if you go to the Kubernetes documentation pages and under task, you have administer a cluster and encrypting secret data at rest. You have these following documents. I'm going to follow this, but also kind of try and explain what we're trying to do. So the first thing first, I'm going to start up a Kubernetes playground. So this is a single node cluster. All right, so this basically is built with the Kuberium tool and has containerd. Okay, so in this video, we're going to look into encrypting secret data at rest. So if you go to the Kubernetes documentation pages and under task, you have administer a cluster and encrypting secret data at rest. You have these following documents. I'm going to follow this, but also kind of try and explain what we're trying to do. So the first thing first, I'm going to start up a Kubernetes playground. So this is a single node cluster. All right, so this basically is built with the Kuberium tool and has containerd. I'm just going to maximize this, and we'll just work on the terminal. All right, so the first things first, I'm going to first create a secret object. So I'm going to do a kubectl create secret. And I want a generic secret, so I'll do that. And I'll probably create a secret from literals. I'm just going to copy this command. Okay, so I'm going to call it key1 and super secret. So that's my secret object. So my secret object is created. So if I now do a get secret, I get to see my secret object. And if I do a describe secret, my secret, I get to see that it's the secret name and the data. If I want to see a little bit more, I do a dash -yaml, and I'm going to do a get secret. Okay, and I get to see the data here. Now, if you look here, so this is key1, and this is kind of the encoded format of the secret. So remember that anyone could take this and decode it and easily view the actual secret, right? So if I do let's see if I have a base 64. Yep, I do. So I'm gonna get that again. So I'm gonna do a echo, copy and paste this. Let's pass it through base 64 and do a decode, and I get to see the secret. Okay, so that's the first thing to know, that the secrets object stored in the secret configuration, as you see it here, is just base 64 encoded. So if you just do a base 64 decode, you're going to see this. So remember not to create your secret definition files and push it to GitHub or something, because anyone could just pick this up and run this command and see the secret, right? So that's the first step. But I want to make it clear that the scope of this video is not really relevant to this encoding here. We are going to focus on the data that's stored within the etcd server. Okay, so this after we are done, this part is still going to remain the same. So we're not really focusing on this part right here. What we're focusing on is how the data is stored in the etcd server. So that's the focus. So let's first look at how this data is stored in the etcd server. Okay, so for that, if you go to the bottom of this, there is this command. It uses the etcd API version 3. It runs the etcd command, passes in the CS certificates for authentication, and we're going to get this particular secret. So the way that it's stored in etcd is stored in registry and secrets and default, and this is the secret name. So let me first see if we have the etcd command line. So we don't have that, so the first step is to get that installed. So I'm just going to do a apt-get install. I think it's etcd client. Yeah, so if you do not have the etcd on, so remember that the etcd server is running in a pod. So you can either SSH into the exec into the pod and then runs etcd command from within that, or if you want to run it locally from your control plane node, you could use the etcd client utility. Now, if the client command line utility is not available, you have different options to install it on different systems. So let me see. Okay, so I have it installed on my machine using the etcd the package etcd client. So look up for whatever it is that the version of etcd that you're running. Okay, so that's there. So now we've got etcd utility. So remember that's the client only. The server is still running on as a pod. So if I do a kubectl get pods -cube system, I have the etcd control plane here, right? Okay, so the next step is to run this. So first, remember that you need the certificate file. So let's see if we have that. Yep, we do. So under etcd, you have all the certificates files needed for connecting or authenticating to the etcd server. So that's good. So I'm going to copy this command. Remember to set the version etcd API version to 3, and the name of the secret is secret1. Let's see what I created. Get secrets. So it's named my secret. So I'm going to replace that with my secret. I'm going to do a my secret. Now, if I just run this command, you can see that it kind of gives me a kind of a jumbled information, but you can kind of see the secret there as is, right? You can see the secret there in a text format. To see it in this format, you just need to append the hex dump to it, because sometimes you may not be able to see it in the right format. So this is the data that's stored in etcd, and if you look closely, you'll see that the secret that I have, the password or whatever it is that I've stored, is actually visible like this. So the data is stored in etcd in an unencrypted format. So anyone with access to etcd will be able to just go through and get all the secrets and other confidential information stored as a secret object. So that's the problem here. So this is the problem that we are trying to solve by enabling encryption at rest in etcd. Now, if you go through this document, the first thing that it says is, first we need to determine if encryption at rest is already enabled or not. So this is done with a property called encryption provider config. So if I go to my kube API server, so let's say my kube API server is running as a process here. And let me just grep for kube API server, and I get to see the kube API server process running with all the options. Let's first see if it has the encryption provider config option. So that's the first thing that we'll do. This is to check if encryption at rest is already enabled. And as you can see, it does not return a result. So that means this option is not configured. We can also kind of verify this. Because this is a kube ADM setup, it uses the var manifest APC Kubernetes manifest. Yeah, ADC Kubernetes manifest. And here you have the kube API server. So if configuration, so if you look at this particular file, let's do a cat, we'll be able to see all the options provided, and here you don't see the encryption option that we have talked about here. So this means that encryption at rest is not enabled. So that's the first step, and we've already verified that by creating the secrets object. Okay, so the next step is to create a configuration file and then pass it in as this particular option. So that's it. So that's basically the steps required to enable encryption at rest. You create a configuration file and you pass it in as an option. So let's look at the configuration file. So this is what it is. So you have the API version, you have the kind, it's encryption configuration, and then you have resources. Now you can pick and choose which resources you want to encrypt, right? So you have pods, deployments, and secrets and services. You want to store all of them as encrypted? You might not, because not everything is confidential, right? So you need not necessarily encrypt and save all the data about pods and deployments. Here our concern is just secrets. So under resources, you specify the targets. So this is secrets. That means only the secret objects are going to be encrypted. Now you can encrypt something using a set of providers, right? So the default one is called identity. Now the identity provider just means that there's no encryption at all. So you can see the list of providers here, and it says the identity provider says there's no encryption. Resources are written as is without any encryption. So and then you have other providers, which are these, and those are listed here. So you have the secret box, you have the AES, GCM, the AES, CBC. So CBC, so all of these are encryption algorithms, different encryption algorithms, and you can see the details about how they encrypt here. So you can choose whichever one you want and provide a key. So this key has a secret. You can provide multiple keys and secrets, and this secret is what will be used to for the encryption by the encryption algorithm, right? Now, one thing to note here is the order. So this, as you can see, providers is a list. So this is the first item in the list, second item in the list, third item in the list, and fourth item in the list. So this order matters because when the encryption happens, it uses this to encrypt, and then it could use any of these to decrypt, right? So always encryption happens with this. So if identity provider, which has no encryption, is the first one, then there's no encryption enabled at all. So that's how it works. So if this is the first one, that means this is what is going to be used for encryption, and since it's identity, it's not going to encrypt anything at all. So if you really want to encrypt the data in etcd, then one of these should be at the top. Okay, so that's the whatever is the first one is what's going to be used for encryption. So let's just do this real quick. So we're going to create a very simpler version of this file, which is this. And this, as you can see, we have specified that all the secrets are going to be encrypted, and we're going to use the AES CBC encryption provider. And as you can see, identity is at the bottom. So the first one is AES CBC. So this is what is going to be used for encryption. Now this requires a secret object, so we could generate a 32-byte random key using this. I'm just gonna copy this. I'm gonna get that key first. So that's what our key is going to be. Then I'm gonna copy this and create encryption object file. So I'll call it enc.yaml, and I'm gonna paste this. Okay, should have copied the secret value first. So I'm going to copy this, and I'm going to go here and replace the secret object here. Okay, so that's that. So now I have the encryption configuration file. It's currently in my home directory. Now all I need to do is go and edit this file. So that's the next step shown here. So in the Cube API server, I'm going to add this line to point to the encryption file that I just created. Then, of course, we need to, since the file is created locally, I have to mount it inside. So I'm going to use volumes and volume mounts. If you have not gone through the volumes and volume mounts yet, then you might want to take a look at that and come back. But this is pretty straightforward. So here you have the directory, the local directory, and that's on my control panel node here. And this directory is going to be mapped to this path within the pod, and then so anything that's available here is going to be available here. That's it, right? So first, I'm going to create this local directory so that I can put my file there. Okay, I'm going to move my encryption file from here to that local directory. Make sure. Yep, so I have the file there. Now I'm going to edit the Kube API server manifest file and then make these changes. Okay, so that's the next step. So I'm going to go into etc Kubernetes manifest and Kube API server. And the first thing that I'm going to do is I'm going to add this line. So this is what tells where the encryption configuration file is. So that's the first step. And then I'm going to go down. So I have two things. I have volume mounts. So this is inside my volume, inside the pod, where it's going to be mounted. So I'm going to copy this. So the local directory is going to be mounted into this path. So that's the first step. And then below, under mounts, I'm going to specify the location of my local directory. Okay, so this is how it works. On my local host, the etc Kubernetes enc directory is going to be mapped to the etc Kubernetes enc directory inside the pod. And then, so since my enc.yaml file is available locally, that file is going to be available inside, and that's it. Okay, let me save that. So now that I've saved and made changes to this file, the Kube API server should be restarting. So let's just give it a few seconds. Let's see. Okay, so this is now, it's now gone. So I'm going to wait for it to come back. Waiting. And if you want to see the status of the Kube API server, since we're using containerd, so you could use the cry-cuddle command. So you could do the cry-cuddle pods to see it's come up. Okay, so it looks like it's ready 3 seconds ago. I'm just going to do, yep, so it's back. Okay, so now let's do a psax and grep for Kube API server. And let's see if it has, just to confirm if it has the encryption. Yeah, so it looks like it has the encryption provider configured. Okay, so that's good. Now what we're going to do is we're going to create another secrets file. So we're going to create a secret object. So we're going to create kubectl, create secret, generic. Okay, and we are going to, let's say, pick this. And this time we'll just create the second one, which is key 2. So you have key 2 and it's called the value is top secret. I'll create that. Oh, my secret already exists. I'm going to say my secret 2, maybe. Yep. Okay, so I now have 2. This is the first one I created. This is the second one I just created after encryption was enabled. So I'm going to go and run the same command as I did previously to check the status of that within etcd. So run this, and the name is my secret 2, and okay, and as you can see, I can no longer see the top secret. So the value was top secret, and I no longer see that here. That means encryption is enabled. Okay, and if I do the same for the old one, I still see the super secret. Now this is because after encryption is enabled, only things that you create newly will be encrypted. Everything that existed previously won't be re-encrypted. But if you update an existing configuration, then that will be re-encrypted. So one of the things that you have here is to ensure all secrets are encrypted. So and what this is doing is basically you're getting the secrets and then just replacing them with the same JSON file. So essentially you're just updating the objects with the same data. So I'm just going to do that. So that's done. And if I run the same command again, I see that it no longer sees the super secret. All right, so that's basically encrypting secret data at rest using one of these encryption algorithms. All right, thank you very much, and I'll see you in the next one.
Hello and welcome to this section on multi-container pods. The idea of decoupling a large monolithic application into subcomponents known as microservices enables us to develop and deploy a set of independent, small, and reusable code. This architecture can then help us scale up, down, as well as modify each service as required, as opposed to modifying the entire application. However, at times you may need two services to work together, such as a web server and a logging service. You need one agent instance per web server instance paired together. You don't want to merge and bloat the code of the two services, as each of them target different functionalities, and you would still like them to be developed and deployed separately. You only need the two functionality to work together. You need one agent per web server instance paired together that can scale up and down together. And that is why you have multi-container pods that share the same lifecycle, which means they are created together and destroyed together. They share the same network space, which means they can refer to each other as local host, and they have access to the same storage volumes. This way, you do not have to establish volume sharing or services between the pods to enable communication between them. To create a multi-container pod, add the new container information to the pod definition file. Remember, the containers section under the specs section in a pod definition file is an array, and the reason it is an array is to allow multiple containers in a single pod. In this case, we add a new container named log agent to our existing pod. Well, that's it for this lecture. Head over to the coding exercises section and practice configuring multi-container pods. See you in the next lecture.